Or to the cloud. Great. Our next speaker is Jonah Klein from Southern Carolina, South Carolina.
Control L.
Great. Thank you.
Does this clicker work? Back. So thank you very much, Mel, for inviting me. Thank you, Mel and Kevin, and whoever else helps in the organization for organizing. It's truly an honor to be here. And I'd also like to acknowledge the support I get from the Canadian government, which is the reason why I can be here in person and not on Zoom. Not in the smoke, yeah. Well, yeah, in the smoke. In South Carolina, I'd be away from the smoke, right? Okay. So let's start with a definition of an arithmetic progression. So if a and m are integers, and I'm going to suppose that m is at least 2, we'll call an arithmetic progression the set of all integers that are congruent to a mod m. So we're dealing with infinite arithmetic progressions. For example, 1 mod 2 is all even numbers, 11 mod 12 is all numbers that are congruent to 11 mod 12. A covering system is a finite set of arithmetic progressions with the property that every integer belongs to at least one of them. So some fairly easy examples that one learns about in elementary school, I guess. 0 mod 2, 1 mod 2, every integer is either even or odd. Every integer is either threeven, throd, or throdder. It's perhaps less obvious that any integer is either 0 mod 2, 0 mod 3, 1 mod 4, 1 mod 6, or 11 mod 12. How do we verify such a claim? Let's do it. So first of all, let's notice that all of 2, 3, 4, 6, and 12 are divisors of 12, and thus will repeat with period 12. And so really what we need to do is verify that a set of 12 consecutive integers is covered by those things. And well, let's just take 0 to 11. That's a nice interval. So let's write them all out, and then let's sieve out by these arithmetic progressions. So we remove everything that's 0 mod 2. We're left with half of what's there. Remove everything that's 0 mod 3. I ported that back up to the top of the slide. Remove everything that's 1 mod 4, everything that's 1 mod 6, everything that's 11 mod 12. You notice everything is crossed out, and so we have a covering system. That last covering system has all the moduli distinct. So these are of particular interest in people who ask questions about covering systems, particularly because Erdős was very interested in them. So throughout the years, there are a lot of problems that were posed on covering systems. And there are 2 problems in particular that really stood the test of time. The minimum modulus problem asks whether or not one can construct distinct covering systems with an arbitrarily large smallest modulus. So for example, that one we had earlier had minimum modulus 2. Can you do that with minimum modulus 100, 1,000, 1,000,000? The other problem that we won't really be talking about that much today is the odd covering problem, which is also called the Erdős-Selfridge problem. Famously, they disagreed about what the solution was. And it asks whether or not it's possible to construct a distinct covering system with all moduli odd. The first one of these was solved about 10 years ago. The last one is still wide open. Well, I think if you look on Erdős problems, there are some people who claim an AI proof, but their lean formalization has holes in it, and they're just saying it's fine, and anyway. So presumably still open. Okay, so let's give a history of the minimum modulus problem, because this is the starting point of what we're going to talk about today. So in 1950, Erdős used a covering system to answer a question of Romanov in now relatively famous paper, because it's in the same paper where he says the following: it seems likely that for every C, there exists such a system, all the moduli of which are greater than C. And by such a system, he means a distinct covering system. So throughout the years that followed, there are many, many researchers who attempted to construct such covering systems. So I'm going to start the history in 1968, where Churchhouse constructed a covering system with a minimum modulus of 9. And this kept on going all the way till 2014, where Owens constructed a covering system with a minimum modulus of 42. The covering system of Owens with minimum modulus 42 has billions of arithmetic progressions. It is not an easy construction at all. The Owens was actually a student of Nielsen who had the previous record, and it was his master's thesis that constructed the 42 one. But yeah, these are incredibly difficult to construct, and actually this Owens was one of the first ones to suggest, because of how difficult a time he had in constructing these, that possibly Erdős was wrong in that claim up there. And in fact, Erdős was wrong. In 2015, Hoff resolved the minimum modulus problem, showing that the smallest modulus of a covering system with distinct moduli is always at most 10 to the 16. This is our starting point. So there are further developments on the problem, and I'm just going to mention that I'm using publication dates everywhere. So if you look at archive dates, it's possible that they're 2 to 3 years earlier everywhere. And since this is so recent, that's a pretty big difference, but I'm using publication dates. Okay, so in 2021, Ballister, Bolbash, Morris, Sarsorbude, and Tiba improved the bound from 10 to the 16 and all the way down to 616,000 with a method that they coined the distortion method. And with that method and surrounding ideas, they solved a number of other problems related. For example, they showed that in any distinct covering system, there's at least one modulus that divides another. They solved the odd covering problem in the particular case where all the moduli are square free. It is not possible. Or else the odd covering problem would be solved. And they showed that in any distinct covering system, the least common multiple of the moduli must be divisible by either 2, 9, or 15. So these were questions that appeared in the literature at some point in time and were all answered by this same technique, essentially. Okay, so and since then, the distortion method actually had a surprising number of applications, at least to me. It's been, yeah, it's been fun to follow, let's just say. Okay, so in 2025, Cummings, Filizetta, and Trifonov showed that in any distinct square free covering system, the smallest modulus is almost 118. So this is basically just brute forcing through the approach and trying to optimize as much as possible in this particular case. In the same paper, they also showed that the jth smallest modulus of the covering system with distinct moduli is bounded, although their proof does not use the distortion method and they don't give explicit bounds either. That last result was improved using the distortion method by me, Koukoulopoulos, and Lemire, where we showed that the jth smallest modulus of a minimal covering system with distinct moduli is at most exponential of Cj squared over log j plus 1. In 2025, Li, Wang, and Yi solved the variant of the minimum modulus problem for number fields. So it turns out you can do the exact same thing for number fields. The distortion method just translates through very well. And basically, it's because if you're looking at the ring of integers, it's a Dedekind domain. You have unique factorization of ideals into products of prime ideals. And you can basically do the whole same thing. With another author, they also solved a variant for polynomial rings over finite fields. They also solved a variant for global function fields. In particular, as a particular consequence of what they proved, they show that there is no distinct covering system of fq of x for q greater or equal to 759. And one of those authors later improved that to 73 by very carefully optimizing the work that they had done together. We're going to talk about one last application. In 2026, Filizetta and Kalogiru solved the problem of Erdős and Selfridge. And they showed that if a covering system has minimum modulus greater than 4, and it's distinct, then the sum of the reciprocals of the moduli is at least this quantity. There's nothing particularly important about that number there. The goal was just to show that the quantity was bounded away from 1, which that's greater than 1. So we have a few questions that kind of follow from this. Question 1, if the minimum modulus is 11, can one significantly improve the above bound? This question might seem random. I will try to convince you from now to the end of the talk that there's actually something going on with 11 there. It's not just a random question to ask. 2, does there exist a distinct covering system using only multiples of 11 as moduli? Somewhat similar to that question above. Again, 11 appears. There are links in between these problems, and we're going to talk about that more. Question 3, what is the largest family of distinct covering systems one can construct such that no two members of the family share a common modulus? So how many covering systems can I build such that no two share a common modulus? So we're going to try.
What does it mean to say that they do not share a common model?
So if I
They're relatively flat.
so I have, let's say I have two different covering systems. There are no modulus used here that's also used here.
Not necessarily.
Yeah, they're all distinct in one, and they're all distinct amongst each other as well. Does that make sense?
Yeah.
Okay. And the name of my talk includes the distortion method, and we're going to go into some detail about what this is. So let D be a finite set of moduli. Let A be a set of arithmetic progressions with moduli set D, where AD is some little AD plus DZ. Let Q denote the LCM of all those moduli, and write Q in its factorization in primes, where the primes are listed in increasing order. What we're going to do is that instead of looking at all the arithmetic progressions at once, we're going to reveal them in stages according to their prime factorization. So we're going to start by revealing the 2 smooth moduli, then the 3 smooth, then the 4, then the 5 smooth, and we're going to kind of build up essentially the complexity of the LCM of what we're considering. Okay, so with this in mind, we'll define Qi to be the potential LCM at stage I of this process, and we'll let B sub I be the set of integers, mod Q, that get covered at step I. At each step I, what we're going to do is construct a probability measure Pi on Z mod QZ, or I wrote on Z mod QIZ, or equivalently on Z mod QZ. We can just extend it. That will measure roughly how well we have covered at step I. The idea is to distort the space so as to accentuate where we're not covering, but without increasing the measure of any point too much. That's the intuition behind it. And the measures are constructed in terms of free parameters, delta I, which are representative of what the distortion will be at a given step. Okay, so a little more notation. Let pi I from Z mod QZ to Z mod QIZ denote the natural projection. And let Fi of X be the fiber lying above X through this natural projection. And let alpha I of X be the proportion of that fiber that gets covered at step I. I think that J right there should be an I. Sorry. The J in the definition of alpha I. Okay. And how we define the probability measure Pi, if alpha I is less than delta I, which is our parameter from which we're distorting, we let Pi of X be Pi minus 1 of X times the indicator function of X is not in Bi divided by 1 minus alpha I of X. In other words, if X is not in Bi, if X doesn't get covered at stage I, we inflate its measure. If X is covered at stage I, we just put the measure to 0. We don't care about that anymore. We're trying to focus on the uncovered set. If alpha I of X is greater than delta I, we similarly introduce some sort of distortion or not, depending on if it gets covered at stage I or not. Once again, I think those should be I's on the right. Sorry about that. Okay, and so those are the probability measures. This is all very technical. So the whole point of these definitions is that they imply the following result. So first, a little more notation. So for a function from Z mod QZ to the complex numbers, we'll denote by EI of F the expected value of F with respect to the probability measure Pi. And we'll let MI of 1 denote the EI minus 1 of alpha I, and MI of 2 denote EI minus 1 of alpha I squared. Think of these as the first and second moments of alpha of I with respect to the probability measure pi minus 1. And with all of the notation from the last 3 slides, the key result of the distortion method is as follows. If the sum of the minimum of the first moments and the second moments divided by that factor 4 delta I times 1 minus delta I is less than 1, then A does not cover the integers. Okay, so basically this is giving us some sort of analytic criterion to determine whether a set of arithmetic progressions is a covering system or not. Of course, this is not really usable yet. We also need bounds on the MI if we want to be able to apply this. And I'll go ahead and put those down here. So a lemma by Ballester and the other authors says that the MI1 is less than or equal to the sum over all D and D, with the greatest prime factor of D being the ith prime, 1 over D. So it's the sum of the reciprocals. That's basically just a union bound. And we have this bound on those second moments, which is a big complicated expression, but that product on the right is some sort of Mertens type product. And so this roughly can be bounded by log of pi to the 6 over pi squared. And so what really matters here is that these first moments for small values of I are actually relatively small. They start growing as I gets bigger, but for I small, those are small. The second moments, when I is small, they could be extremely large, but they have quadratic decay. So that's useful. To illustrate why the 3 bounds that I just listed are useful, let's go ahead and give a proof of Hott's theorem in one slide. Okay, so the sum right here, which is essentially it's the bounds on the second moments, where I took delta I to be 1/2. That sum is convergent. I mentioned that the expression inside there is essentially quadratically decaying. That sum is convergent. And so we can find some integer k such that the sum over I larger than k is bounded by 1/2. Okay, so the second we use second moments to take care of the tail, essentially. For a given set of moduli D, all of which are greater or equal to m for some fixed m, we can work out the following inequalities. So right here, what we have on the left is the bound, the sum of the bounds given on the first moments in the previous slide. This is just equal to the sum over all pk smooth 1 over d. Sum of d and d that are pk smooth. And because we assumed all d and d are at least m, this is bounded by the sum of all reciprocal pk smooth numbers that are greater than m. In particular, if we choose m large enough, we can make that last sum smaller than 1/2. And so the sum over the first few terms is bounded by 1/2. The sum over the last few terms is bounded by 1/2. And so the entire thing is bounded by 1. And so by that key result by the distortion method we had earlier, no covering. Okay, so very, very powerful results. Okay, let's get back to our problems now. So let's start with what I consider the easiest of the problems. So what we managed to prove is that there are no distinct covering systems using only multiples of 11 as moduli. So that cannot be done. The idea is really just a pretty much direct application of the distortion method. We give bounds on the first and second moments. First moments are for the initial terms, second moments are for the tails. And if the bounds are correct, well, if we get a bound of 1, we win. Okay, so for first moment bounds, we go up to the 18th prime, and we get this bound, which we can compute simply by noticing that the sum of the reciprocals of smooth numbers can be written as some sort of Euler product, and we can compute it directly to get the bound that I just wrote there.
What is 11?
I'll get back to that. Basically, you can't make the argument work for 10. 11 is the smallest one for which we were able to get the argument to work.
But it also automatically works for 13, 17, 19, or all the bigger problems.
Yeah, exactly. And I'm guessing we can probably get it to work for 12, which would imply a whole bunch of other numbers. And probably we can just get it to work for everything greater than 11. It would take more work that I have not done, but I do believe it should be the case. Okay, now we need to bound second moments. So we bound second moments in two different parts. We start by going up to some threshold that is purely computational. And what we do is essentially compute the bounds for that sum and optimizes our choice of delta I numerically. And what we get is that that's smaller than 0.235555. Okay, and finally, we deal with our tails. That, as I mentioned, they have quadratic decay. So if you work out the finer details, you can show that actually the sum of the tails is bounded by 0.00003. Okay. So I didn't mention what the delta i's are. We have these distortion parameters. So in general, when you apply the distortion method, you apply no distortion as you use first moments. You start distorting your space when you get to using second moments. So we let delta I equal 0 for I less than 19, meaning that there is no distortion introduced at this stage. For 19 less than or equal to I less than 10 to the 5, what we did is that we chose the deltas in order to numerically minimize this. It's possible that our numerical minimization is a local minimum and not a global minimum, but it managed to work. And together, if you sum all the bounds that I put there, that's smaller than 1. And so by the key result of the distortion method, it's not a covering system. There are no covering systems with multiples of 11. Distinct multiples of 11. All right, next problem. Okay, so recall that we asked the following question. If the minimum modulus is 11, can we significantly improve that bound of, that was something like 1 plus exponential of minus 10 to the 21? What we managed to prove is the following. So if C is a distinct covering system with minimum modulus 11, then the sum of the reciprocals of the moduli in C is at least 1 plus 1 over 11 times 10 to the 30. So we went from exponential minus 10 to the 21 to 1 over 10 to the 30. Massively better, yeah, even though still extremely small. Yeah, and so the key observation proving that result is the following. I just want to note that a similar observation was made in that initial paper of Filzen and Calgi wrote. This is not new. So suppose that we have a covering system C that has minimum modulus 11, distinct moduli, and sum of reciprocals bounded by 1 plus C for some fixed C greater than 0. Suppose D is a modulus with 11 does not divide D. Then D is greater than 1 over 11C. Essentially, if 11 doesn't divide D, D is coprime, they have to intersect, and that intersection forces the sum of the reciprocals to be large. So there can't be very large intersections, which is what that's saying right there. So I'm going to give a rough sketch of the proof of the theorem. So we're going to split up the moments according to whether or not the moduli are divisible by 11. In the case where they are divisible by 11, where we already did that. That was the previous problem. In the case where they are not divisible by 11, we have that lemma that tells us, well, those that are not divisible by 11 are actually very large. And so we can actually do some type of minimum modulus type computations, because we know that all the moduli that are in that part are very large. Now I'm sweeping a lot of things under the rug here, because in particular, second moments are not linear. You can't just split them up according to the moduli depending on what divides what. But that's essentially the idea behind how we get such a result with a lot of messy computations. Okay, we had one last problem that we talked about. So recall that we asked, what is the largest family of distinct covering systems? What can construct such that no two members of the family share a common modulus? In my abstract, I called those disjoint distinct covering systems, which is what I'm going to call them now. So let n denote the size of the largest family of disjoint distinct covering systems. There's not that much known about it. On one hand, there's a construction of Harrington that shows that n is at least 3. He gives an explicit construction. On the other hand, the bound on the minimum modulus implies that n is bounded by 615,999, simply because every one of those has the smallest modulus. They're all different, and they're in between 2 and 116,000. That's not a very nice bound. We managed to improve that to the following. N is actually smaller than 10. Okay. And the following lemma is actually how we get that result. So suppose one can construct a family of 10 distinct disjoint covering systems. So suppose that other result was false. Then one can construct a covering system using only distinct multiples of 11. So once again, that 11 is coming back. And I'll leave the proof of this lemma as an exercise for the interested member of the audience. I'd be glad to talk about it later, if anyone is interested. I'll try to stimulate your interest a little. Okay. So let's maybe talk about further problems. Okay, so we know by those bounds that n is somewhere between 3 and 10. What's the actual value? I guess worth mentioning, lower bounds essentially amounts to building examples. Perhaps that lower bound can be improved by one with all these AI things going. Apparently AI is really good at constructing these examples. A lot of people have been throwing a whole bunch of problems at AI. Perhaps you can get n equals 4 here with your large language models. Perhaps not. It is that the construction by Harrington that achieves 3 is pretty hard. But who knows? Maybe worth a try. And also, I mean, as I was saying, why is 11 special? Well, we weren't able to get the argument to work for 10. So can you do it for 10? I would expect not by the numerical evidence I have, but we don't know. Thank you.
Thank you.
Yeah.
Is this problem on the last slide, is that substantially different from asking for a system of moduli, a system of congruence classes with distinct moduli where every integer is in at least n of the
So it's easier to construct what you're saying, I guess. Yeah. Wait, can you?
Yeah, so this seems a little bit harder, right? Because this is actually asking for you to be able to partition the congruence classes in different sets where each one is a cover.
Yeah. Yeah, it is harder. Yeah. But what you're asking is what can be said about the case where we just want integers to be covered n times, but we don't care about them being covered by just different.
Is that the same problem, or is that
It's not the same problem. It's as initially I was trying to work on that problem and I ended up on that one. That probably answers your question indirectly.
Other questions for Jonah?
Yeah.
What about distinct disjoint systems of square-free moduli? Can you get an upper bound that's better than 10 for?
I would imagine we can do much better than 10. Yeah, I would guess it's 1. Yeah. Simply, there are no known covering systems with square-free moduli with minimum modulus greater than 2, which is why I'm saying that. So in particular, if you want to have a family that has more than 1, you need one of those. So yeah, it's actually, I think there are people who conjecture that there are no such, yeah.
Other questions on Zoom or elsewhere? Not, let's thank Jonah again. Maybe you could give Steve back there a couple of your problems that you could put on the list.
Yeah, I have other problems too to put on that list.